All right, so today we have the real case of the voltage amplifier. So what are we talking about here? This is the case where the feedback system does not exactly mirror the block diagram that we started with. So the block diagram that we started with and the equations that we derived for the various types of amplifiers had some assumptions, such as the signal source does not have a source resistance. So in this case, the voltage source here, in the ideal case, would have zero resistance in series. The load, there was no load. So in the case of the voltage amplifier, we assumed that this RL is an open circuit. And we also assumed that the feedback network is kind of ideal. If we connect it across the output, it would not affect the output, and some other things that we implicitly assumed, but now we will no longer assume. So we will consider a signal source with a source resistance, VSRS or Vsig Rsig. We will consider that there is a load connected, and we will consider that the feedback network is a real circuit that may affect the basic amplifier and the rest of the feedback network of the feedback loop when we connect it. So how do we do that? How do we model such a feedback network when we connect it to other circuits? By the way, the word or the term network in circuits and electronics means circuit. It doesn't mean a computer network or whatever. It means just circuit, feedback circuit. All right, so here's my feedback network, and in circuit theory, this is called a two-port network because it has two ports, a port from this side and a port from this side. The basic amplifier is also a two-port network. It has a port from this side and a port from this side. This is the input and this is the output of the basic amplifier. So given that these are two ports and that we want to find the characteristics when I don't have the ideal conditions, what tools can I have? If I want to consider this to be a two-port network with this being port 1 and this port 2, and I want to find the input resistance of this feedback amplifier and the output resistance of the feedback amplifier, how can I make use of what I know so far and also what I know from circuit theory? In particular, there is a complete theory on two-port networks, two-port circuits, and we can use it in this case, in the case of the feedback network. And this theory is actually quite simple. If I have a one-port network, if I have a circuit and I want to model it and simplify it, if it's a one-port circuit, and let me draw a one-port circuit. So this is, say, my one port. It's a box. Inside the box, I have all kinds of circuit elements. Like in our case, we're interested in resistors and voltage sources and current sources and simple, no strange circuit elements. If this is a one port, because it just has this one port, and I have all kinds of circuit elements here, then there is a very powerful theorem called the Seventh Theorem that says that all the complexity that's inside, I can model it by just a V-Thevenin R-Thevenin, just a voltage source in series with the resistor. And this would actually model the one port, and it's a complete model. It's a full model as far as whatever is connected to this, they will weather this real one port is connected, or its model, its simplified model V7 and R7 is connected to the rest of the world, they would not know the difference. So V7 and R7 are a complete representation of this as far as the rest of the circuit is concerned. And that's a very nice result, because I may have here tens of voltage sources, hundreds of resistors, and all of that I can simplify and replace by just one voltage source and one resistor. That's the Seventh Theorem. And this is called the Thevenin equivalent. So for the two-port network, we can kind of extend the Thevenin theorem and say, from this side, maybe I can have some Thevenin equivalent, and from this side, maybe I can have also a Thevenin equivalent, like a resistor in series with a source here, and a resistor in series with another source here. And the two resistors and the two sources can then model whatever is inside here. And what's inside may be complicated, and I would just replace it with two resistors and two sources. One resistor and one source from this side, and one resistor and one source from this side. And this, in fact, is possible using the two-port network theory. So this is the two-port network theory applied to model the feedback network in the case of the voltage amplifier. You may find this terminology strange now, but that's fine. We will not use it a lot. We'll just use it probably on this slide. In two-port network theory, as we said, we can simplify, we can model the feedback circuit, or any two-port for that matter, by two resistors and two sources. One resistor here with a source, and one resistor here with a source. So a resistor at port 1 and a source at port 1, a resistor at port 2 and a source at port 2. So think of this as the Thevenin from this side and the Thevenin from this side. But notice that on this side, on port 2, in this case, I am using what's called the Norton equivalent, a current source in parallel with a resistor. And that's for convenience, because I'm using a voltage amplifier. And two-port network theory, I can have different combinations, like a Thevenin model here and a Thevenin model here, or Thevenin Norton, like what we have here, or Norton Norton, or Norton Thevenin, and different kinds of combinations. All of these would work. For the case of the voltage amplifier, the most useful is called the H parameter model. H11, H12, H21, H22. So this set of parameters would model the feedback network as a series, a Thevenin type from this port, and a parallel Norton type from this port. And this will be a resistor, we call it for now H11, in series with a voltage source, and this will be a resistor, but in parallel with a current source. Now, for some approximations and some movement around of these two resistors. Okay, let's consider H11. Here's what I will do to H11. I will push it. I will push it with the laser. So I will push H11. Okay, so follow the push. H11 is moving up all the way to here and put it here. All right, so this is H11 now. I pushed it up to here and put it here. I can do that. H22, I also push it. So push, it goes to here, push up, and then push inside. Eventually, it will appear here. So I pushed it all the way to here, and here it is. So H22, push it to here, and here it is. H11, push it to here, and here it is. H12V2 stays there. And V2 is VO. V2, the voltage here, is the same as VO. So H12 VO. And now we're left with H21 I1. And here's an approximation that we will do. The approximation is the following. Any forward transmission in the feedback amplifier is through the basic amplifier only. Any reverse transmission in the feedback amplifier is through the feedback network only. This is an important assumption, and we will need to use it. So all the forward transmission is only through the basic amplifier. All the feedback transmission is only through the feedback amplifier. And if you remember the first slide, maybe in this feedback chapter, we had an A with an arrow in this direction above it, and a beta with an arrow in this direction above it. And we said at the time that this is the signal flow direction. So all the forward signal flow is only through A. All the reverse signal flow is only through beta. We have to use this assumption in order for our feedback study to hold without a large error. All right, so if this is the case, and we consider now this element, what is this? This is taking a I1 here, the current flowing here, and multiplying it by H21 to produce a current here. So this is a forward transmission in beta and the feedback network, because it takes I1 from here and produces a current here. Look at the direction. This is an invalid direction. We're not supposed to have that. And that's why we will assume that this is negligible. Now, in reality, it's there. It's not negligible. But the error that it will introduce would be very small, because in reality, most of the forward transmission would be through the amplifier. And this, if we just remove it, would not introduce a large error. So we will do that. We will go with the assumption that all of the forward transmission is through the basic amplifier, and all of the reverse transmission or feedback transmission is through the feedback network. So I'll remove it. And now there's nothing here. So there's nothing here. H22 is now here. This, I removed it. I made it 0. Now it's an open circuit. H12VO is here. H11 is here. So now I will stop using the H terminology. I'll just call this R11. It's a resistor, so why call it H? And this, I will call it R22. Okay. These are two resistors, R11 and R22, and we get them from the feedback network. And this is the voltage here divided by the voltage here, and this H12 is then just the beta that we've been using since we started the discussion of feedback. So now what do we have? Once I do this with R11 here and R22 there, and this becoming my beta circuit, notice that I am back to the ideal case. I am back to the case where this is ideal, because when I connect this, it won't affect the output here because it's an open circuit. The open circuit will have no effect on the output. And it's producing an ideal voltage, and this is an ideal source, and everything else is now inside this gray thing. So what is this gray thing? This is the basic amplifier, but I add to it, I augment it with the signal source resistance, R sig, R11 of the feedback network, the load RL and R22 of the feedback network. And I call this now the augmented A circuit. So A augmented. Why is it called augmented? Because I added to it four things, four resistors, RS or RSig, R11, RL, and R22. Now, the basic amplifier and the four resistors, that's called my augmented A, my augmented amplifier. And this augmented amplifier, I can now treat it as if it's a new A circuit, and I find its characteristics, basically its gain, A. And then I can use the equations that I derived for feedback, assuming ideal conditions, like no RSig, no effect of this on the low, on the gain of the amplifier, and that should work. So how do we get these R11, R22, and A of the augmented amplifier? All right, because here I need R11, and I obtained this from the beta network, and R22, I also obtained it from the beta network. And of course, I need beta. And once I have R11 and R22, I need A of the augmented circuit. So there are procedures to find these from two-port network theory first. Let's start here. R11, I take the feedback network, and R11 is the input resistance here at port 1, the resistance seen looking into port 1 with port 2 shorted. Right? That's from two-port network theory. R22 is the input resistance or the resistance seen looking into port 2 with port 1 open. That's R11 and R22. They're actually simple, easy to calculate. So you short port 2, you just take the feedback network, look into port 1, and the resistance that you see is R11. Same here, except that port 1 is open and you look into port 2. Beta, how do I calculate beta? Beta is VF over VO. So you open circuit here, you open circuit port 1. This is the feedback signal here. This is the output, and you insert the feedback network between the source and what you want to measure here. So VF over VO that we would calculate from the feedback network would be beta, assuming that I have an open circuit here. So that's how we calculate beta, R11, R22. Now, how do you calculate A? And remember that A is now for the augmented, not just the basic amplifier, for the augmented amplifier. So A is the gain from here all the way to here. And this is just another amplifier, and it should be simple to calculate, really. So just our basic amplifier with two resistors here across the output, and RS and R11, and the input is between them. And that's the augmented A circuit. We calculate the gain VO over VI here, and that's A augmented. And now we use A augmented and beta to find A with feedback. So AF would be A augmented over 1 plus beta A augmented. And this is the procedure, this is the algorithm. So you find R11 in the case of voltage amplifiers. The input resistance of the feedback circuit at port 1 with port 2 shorted. R22, input resistance of feedback circuit at port 2 with port 1 open. Find A augmented, VO over VI from modified A circuit with the 4 additional resistors. Find beta, VF over VO from the feedback circuit with input at port 2 and open circuit at port 1. And now I have all the quantities I need to find AF. So AF, the gain with feedback would be this. I can use now the formula because of this trick that I did with the A circuit, and I augmented it with the 4 resistors. And that's the gain with feedback. What if I want to find the input resistance and the output resistance of the feedback amplifier? Well, I can also use the feedback formulas. So I find the input resistance of the augmented A circuit, including all the 4 resistors. I find the output resistance of the modified or augmented A circuit, including the 4 resistors. So here, this RO is special. Why is it special? Because all the resistors are inside. Remember, back in the days, we used to say, never calculate an output resistance with the load connected, right? Now, for this trick that we're doing here, actually the load is now part of the circuit, and we don't disconnect it. We keep it, and we find the output resistance. And also for the input resistance, the signal resistance is inside. But now you will notice that we will do a correction at the end and remove them back. So we find the input resistance of the modified A circuit, including RSig. We find the output resistance of the modified A circuit, including RL. And we apply the feedback formulas for input resistance and output resistance in the case of voltage amplifier. And this is the equations that we derived. The input resistance increases by 1 plus beta A. The output resistance decreases by 1 plus beta A. All right. However, that's not the final result. The final result, I need to correct now this. And from the input resistance, I need to remove RS. So back here and here, the input resistance is actually here. Right? I mean, this is the signal source. And the input resistance is here. The quantity that I calculated was here. RIF was here. I want this because this is part of the source, really. I calculated a quantity here. That's not what I want. I want here because this is part of the source. So how can I correct? Well, it's easy. Just subtract RS. And this will give us the resistance after RS, after RSig. That's what we want. This is, we call it RN. What about RL? Again, this is the RL, but it should not be here. When I calculate the output resistance, I'm getting the output resistance of everything here. So this is the output resistance with feedback. I need to remove this, move it behind the output resistance that I want. How do I remove a resistance in parallel? I subtract 1 over. So the output resistance, R out, will be 1 over ROF minus 1 over RL. So this equation says that I am moving back RL behind the output resistance, and this would be the case. So we need to do these corrections for input resistance and output resistance to get correct values. Let me pause for a few seconds here to see if there are any questions. Let's do an example. And here's a nice voltage amplifier with feedback. All right, so this is our amplifier. 2 Mosfets, 4 resistors. All right, so this is the VSig. Notice that I don't have RSig here. So the signal source is kind of ideal. And that's the output. And there's no load connected, so I don't need to worry about RL here. But there is feedback. And you see the feedback. You see how we are taking the output and feeding it back towards the input. That's feedback. And where's the feedback signal? The feedback signal is here, V feedback. And what is this V feedback? This is equal to the signal here at the source of M1. And Vsig is at the gate. All right, so this must be my beta network producing VF from VO. That's beta. So it takes VO to ground, produces VF. That's beta. Now, this I need to subtract from VSig, VF. How am I doing the subtraction? Yeah, because VGS is an important quantity in the MOSFET, and the current here, ID, is GM VGS. The signal current and the drain is GM VGS. I'm neglecting small RO for the MOSFETs for simplicity now and to make it to just focus on the important things. So let's not consider small RO for the two MOSFETs. The current here, ID, will be GM VGS. GM VGS. And this is the trick I am playing to find the difference between the source or the signal here and the feedback. This is VG, VGS is VG minus VS. So because the drain current in the MOSFET is GMVGS, the MOSFET for free is giving me the subtraction operation, the difference operation. I don't need to do anything, just connect the feedback to the source and the signal here to the gate, and the current here would be proportional to the difference, and therefore I get the difference for free. That's so the sigma, the subtraction, is embedded inside the MOSFET, and that's great. Okay, so this is VGS here, and this gives me the difference between the signal source and the feedback signal. This is a common source amplifier. So if I go from here to here, there's a minus sign. And then this is another common source amplifier. If I go from here to here, another minus sign. And therefore, A is positive. If we want to show that the feedback is negative, A is positive, and beta should be positive. So now let's follow the algorithm on the previous page. If I have a voltage amplifier, what are the steps? Find R11 and R22. Input resistance of feedback circuit at port 1 with port 2 shorted, and input resistance of feedback circuit at port 2 with port 1 opened. So this is the feedback network. I'll redraw it here to find R11 and R22. That's my feedback network, R1, R2. This is what we call port 1, and this is what we call port 2. So what is R11? R11 is, let's change the color to blue, and this is R11. And when I want to calculate R11 from the previous slide, notice that we say port 2 should be shorted when we calculate R11. So I need to short port 2 when I calculate R11. And if I do that, what is the resistance seen looking into port 1? I have R1 now in parallel with R2. So R11 is therefore R1 parallel R2. That's R11. What about R22? R22 is the input resistance of feedback circuit at port 2 with port 1 opened. So I'll keep it open and find the resistance looking into port 2, and I won't change anything at port 1. I'll keep it open. So this is R22. So what is R22 in this case? If I'm looking into this, I see R2 in series with R1 now. So R22, because the port 1 is open, R22 is R1 plus R2. So these are the two resistors that I need, R11 and R22. I also need beta. So I also need to find beta, which is V1 over V2 with port 1 open, or VF over VO with port 1 open. And if port 1 is open, and I want to find V1 over V2, then this is like a voltage divider. V1 over V2 would be R1 over R1 plus R2. That's beta. And notice that beta is positive, and we said that A is positive and the feedback is negative, right? A is positive because I have two common source amplifiers cascaded. Each has an inversion, each has a negative gain, but when I go over two of them, A would be positive. All right. So now we have beta, we have R11, and we have R22. The next step is to build the augmented A circuit. So the augmented A circuit, I remove the beta, I remove the feedback. The augmented A circuit has no feedback in it. I remove this. And instead of beta, I replace it on the port 1 side by R11 and on the port 2 side by R22. So I don't have any, okay, went to the wrong slide. I don't have any feedback now. I removed the feedback. So the augmented A circuit is a regular amplifier without feedback. This is gone. So now I have R11, R1 parallel R2, R22, R1 plus R2. This is from the port 1 side, and this is from the port 2 side. And now I get my augmented A circuit that has no feedback. This is it. That's the augmented A circuit. As you can see, it has no feedback, just two regular common source amplifiers. So now we find the gain of this, A augmented. So what is A augmented? A aug, that's the gain of the augmented A circuit, this circuit, where there's no longer a beta here, there's no feedback. It was replaced by R11 and R22. Well, this is, let's call this Vx. The nice thing about MOSFETs is that when we connect them, they don't load the previous stage if the connection is at the gate. So I can find Vx over Vsig, irrespective of the second stage, and then V out over Vx and multiply them because they don't load each other. So Vx over Vsig, and that's the gain of a common source amplifier, times V out over Vx. So what is the gain of a common source amplifier? Oh yeah, remember that formula sheet about the gains of MOSFET and BJT amplifiers. We can consult it, and for a stage like this, which is the common source with a source resistance R11 now, notice that R11 is a source resistance for M1, resistance between the source of M1 and ground. The gain is given by minus GM1 RD1 divided by 1 plus GM1 R11, 1 plus GM1 RS. RS in this case is R11. So that's the gain of the first stage, this. What about the gain of the next stage? There's no resistor between the source of the MOSFET and ground. So it's minus GM R prime L. And what's R prime L? It's RD2 parallel R22. This R22 and RD2 appear in parallel in signal analysis. So times minus GM2 RD2 parallel R22. Okay. So that's A augmented. I took into consideration here in R11 and here in R22 the effect of the beta network to find A augmented. Now, what is the gain with feedback? AF would be A augmented, and we know what this is. A augmented, divided by 1 plus beta, A augmented. And we found beta on the previous slide. So beta is here, that's beta. We take this and plug it here. A augmented, we just calculated it from the two common source stages. And this is the gain with feedback. I can also calculate the input resistance and the output resistance. The input resistance, I don't need to calculate really, because whether there is feedback or not, there's no current into the gate. So the input resistance would be infinite anyway, without feedback or with feedback. What about the output resistance? The output resistance is, in this case, RD2, as we said, we consider everything. Even if there is an RL, we include it, but there is no RL now. So the output resistance in this case would be RD2 parallel R22. And the output resistance with feedback would be this, divided by 1 plus beta A augmented. A augmented. All right, and I don't need to do the correction to remove RL, because there's no RL to remove.